What?
Party?
That's your comment?
Well, almost. We could have food in the shape of condensers.
Good one.
Done with
Brownies.
All right.
Okay.
Or soup. We could do volume of soup.
I keep hearing noises at the door, like someone's trying to get in or something.
oh wow.
Okay. Oh, okay, we'll go with that. All right. So now we have this surface. Z is equal to 1 plus 3x plus 2y squared. And x and y now is no longer confined to a rectangle. So what we have is x and y come from a triangle with these vertices, 0, 0, 0, 1, and 2, 1. All right. Now in this case, if you let x and y be the parameters, then what you end up getting is our u is going to be 1, 0, zx. Our v is 0, 1, zy. We kind of went through this before. So the magnitude of Ru cross Rv is going to turn out to be square root of 1 plus dz dx squared plus dz dy squared. So now the area, you're going to integrate over the triangle, which we'll get to in a second, this function, 1 plus dz dx, which is 3, plus dz dy, which is 4y squared, 12. dy dx. Now, there's two ways you can integrate it. One is making y the inner variable and x the outer. So if x is the outer variable, you're going to go from 0 to 2. And then for y, your limit will be x over 2 up to 1. So that's one way you can do it. But this whole thing turns out to be square root of 10 plus 16y squared. Now, how would you go about integrating something like that?
Substitution.
What?
By substitution.
There is a substitution. What kind of substitution though? Drake substitution. It's going to get kind of ugly. The numbers don't work out nice either. Don't do it. I started and it's like, you know what, this is ridiculous because you can go the other way. Do x first. So now y is going to go from 0 to 1. And then x is going to go from 2y, or from 1 to 2, from 0 to 2y rather. So now those will be your limits. Now you're still going to have the same function, of course. 10 plus 16y squared dx dy. But how come this integral is going to be so much easier than trying to do this? What's going to happen as we go through this process and integrate with respect to x?
Well, the integration with respect to x, you just add an x because there's none there.
Yes.
And then you could use the substitution.
Yeah, so we're going to end up with is when you integrate, you're going to get x times this, and then you plug in these limits for x. So now you're going to get the integral from 0 to 1 of 2y square root of 10 plus 16y squared duy. This is much easier to handle than this, because what can we do now?
Just let u equal whatever's under this radical.
Yes, you make a u substitution. U is equal to 10 plus 16y squared. So du is 32y dy. So that's going to absorb this y, and we'll get a simple integral involving u to the 1/2, which you could do. So something to keep in mind. Also on the remaining tests that you have, that it's possible I might rig an integral so that if you do it one way, it's going to be a real pain, but if you do it the other way, it becomes a lot easier. So, same thing applies to these theorems, like Green's theorem, Stokes' theorem, etc. Suppose say I could give you a problem that's just integrate this vector field over this curve. Well, you could try doing it over a curve directly. There's a formula for that. It might be reasonable. But it might be more reasonable to try applying Green's theorem to get a double integral, and that double integral might turn out to be easier. So these are the things to look out for.
How would you know in those specific cases when to apply one or the other? Just when we start working it and realize it's really difficult? Or?
Yes. Like when you get something like this, this is good incentive to back up and consider whether there's something else that can be done. Yes, this is doable, but no. Trust me, I know. All right. Now, in the little time we have left, we'll say a little something about what I mentioned earlier, surfaces of revolution. So if you have this parameterization, you're involving y equals f of x revolved around the x-axis. And A goes between x and b. So you have this curve, y equals f of x, and then revolve it around so you get some really dorky vase. So in Calc 2, you study surfaces like this to compute volume, but you use similar ideas to compute the area. So we have a parameterization, x is u, y equals f of u cosine theta, z is equal to f of u sine theta. All right. Or actually, I'm using v in the notes for theta, so I'll just keep it the same. All right. Now, so now what you can do, so u goes between a and b. V goes between 0 and 2 pi. So you compute your vectors. So we have 1, f prime of u, cosine b, f prime of u, sine b. Rv is 0, minus f of u sine, f of u cosine. So now you can compute the cross product of these. All right. And what you're going to get is f prime cosine squared plus f prime sine squared v for your first component. For your second component, you're going to get 0 f cosine b, and then for your third component, you're going to get minus f sine v. So now the magnitude, so this simplifies to f of u, f prime of u. So now when you compute the magnitude of this, you're going to get the square root of f prime squared plus f squared cosine squared. Yes, I'm being horribly abusive with my notation, deal with it. To see how things simplify. So now what we get is these simplify to f squared. So now we have a square root of f squared, f prime squared plus f squared. Factor out an f, so we have absolute value of f, square root of 1 plus f prime squared. So now we can write down a formula, a more specific formula for the area of such a surface. So we don't have to fall back on cross product of RU magnitude of cross product of RU and RV. We can write everything directly in terms of f. So the area